All right, so I put up on the slides the multiple choice questions you requested, and then I also put up the paper 2, question 3, because that was the most requested one. But I am going to do a screencast going through all of the paper 2 questions. So, I will post that. It will probably not get posted until tomorrow, hopefully tomorrow by the afternoon. And I will make an announcement when I post it. So we're going to start. I want to start with going over yesterday's warm-up because we didn't finish going over yesterday's warm-up, right? So we're talking about enthalpy cycles and equations for the different ways that we can use Hess's law some of the different ways that we can use Hess's law to find the enthalpy of a reaction. So generally speaking, if you are not understanding the enthalpy cycle thing, I'm going to try to explain it in a way that hopefully will make sense. So we have our reactants going to our products. The top of the enthalpy cycle is always the reaction we're interested in. That's the one, well, not always, but most of the time, it's the reaction that we're interested in. You may be asked to solve for something else in the cycle, but this is the reaction of interest, okay? We can get there doing this reaction, but we cannot get the enthalpy directly from doing this reaction. Or maybe this reaction is not possible, but we still want to know what the enthalpy change would be if we could do it. All right. And so what we're going to do is we're going to take another route to get there. We're going to take a detour. All right. And since we're starting in the same place and ending in the same place, the total change in enthalpy, the net change, is going to be exactly the same, even though we're taking a totally different path. So whatever this is, okay, down here, we're always taking this route, going down to whatever our alternate stop, our like pit stop is, and then going up to the products. So this is always the route that we're taking when we write the equation, okay? So the equation that we write, and whether it's reactants minus products or products minus reactants, depends on how we get from our reactants to our pit stop and how we get from our products to our pit stop, or vice versa. All right, so if both of my arrows are pointing up, so from elements in standard state, I'm going from the elements to my reactant substances. And I'm going from the elements to my product substances. And I have a delta H here, and I have a delta H here, and these are known. What I don't know is across. Okay? So this is always my target that I'm looking for, okay? What type of standard enthalpy am I using in this example? Yeah, formation. This is formation, okay? We are forming the substances. So both arrows are pointing up, right? But my path is still down, down, and then up, right? My path is still going like this. So in this case, my reactants, the up arrow is opposite to where I need to take the path. So this is going to flip the sign. This is not going to flip the sign. Now, that's not to say it's necessarily going to be positive or negative. It's just we're flipping this, whatever we're given, we're flipping that sign on the reactants, which is why we write this as the delta H of our reaction is the sum of our products, which is positive, minus the sum of our reactants. again, it's not that the enthalpies are necessarily positive or negative. It's that we're flipping the sign of our reactants. So we're subtracting the total that we get for our reactants, and we're adding the total that we get from the products, which is why we write it as products minus reactants. You could write it as negative reactants plus products, as we saw yesterday, right? That is formation. We are forming the substances, both arrows are up. Okay? All right. We are using enthalpies of combustion, we are burning both the reactants and the products. We are destroying them. So both arrows are down. But my path is still going like this. My path is always going like that. Okay? So I have my delta H over here, and I have my delta H over here. My path stays the same. So I am going to, because the path stays the same, this is going to be not flipped, and the products are going to be flipped. Yes?
Is there a reason that you didn't draw an arrow from R to B?
No, there is not. Sorry. Yeah, question mark. Okay. All right, so then my delta HR is going to be the sum of my, now in this case, my reactants are positive, so I'm adding my reactants, and I'm subtracting the products. Okay? So this is combustion. This is formation. But the path that we're taking through the cycle is always the same. Okay. Does that help a little bit? Okay. Okay. You can thank Hannah in first period for making me realize that was talking about the path was a better way to do this. Now, when we're talking about bond enthalpies, we're talking about, it's easier to visualize it in a reaction diagram where we have our reactants and bonds breaking, which is endothermic and therefore positive, okay? Are let me actually not write elements because that makes it sound like formation, but individual atoms. It is not. Oh, it is kind of like that, but it's not, because this is not how reactions actually go. The activation energy is usually related to the formation of an intermediate, but this is not the intermediate that would be formed in almost any reaction. Okay, we're not going to just break all the bonds and then form all the bonds again. We're usually going to break some bonds and form other bonds. So, it's the idea that we have to put energy in order to get energy out, in order for the reaction to take place. Yes. Question? Okay. Yeah. All right. So then, our products. This is bonds forming. Okay. That is exothermic. It releases heat. Remember that the thing about when the atoms are separated here and they're bonded here, our potential energy is lower. That change in energy is what we're releasing when we form the bond. Okay, so bonds forming is always exothermic, and therefore it's going to be negative. Now, the relative height of the reactants in the products tells us whether, as a whole, the reaction is exothermic or endothermic. I deliberately sort of wrote them on the same levels to not try to say that this is a particularly endothermic or exothermic reaction. It can go either way. If our reactants start higher than our products end up, that would be exothermic. If it's the other way around, it's endothermic. But that's like this difference between the start and the end. When we are talking about theoretically breaking all of the bonds and forming all of the bonds, the breaking is always endothermic, the forming is always exothermic. So this is going to be the bonds broken, which is our reactants, minus, because this is negative, bonds formed. Products. Okay. All right, so let's go through the questions you asked for. And I will post these slides. Number 5, enthalpy of formation of ethanol. Somebody who understands this question, want to explain it for us? How you answered this question? This is question number 5, multiple choice. Multiple choice, question number 5. Yeah, go ahead.
Because you're looking for 1 mole of ethanol.
That's right. Can't be B or D.
It can't be A. You said this would not be on the test.
Yeah.
I know this already, but ethanol has to be a liquid. So
Yeah.
it can't be a gas. It would most likely be a liquid.
Yeah. So, I mean, it could be a gas if we heated it up enough, but yeah, it is the standard state of ethanol is liquid. When we get into bonding and intermolecular forces, you will understand why. It's because it has this OH group, which is very polar, and so the molecules are going to hang together because of their positive and negative ends, and so it's not going to separate out and become a gas unless we heat it up. All right. Any questions on that? Okay. Number 6. This one is tricky for a couple of reasons. One, I didn't give you the structures. I promise that on the test, I will give you structures for including multiple choice questions that require bond enthalpies. I gave them to you for the paper too, but I did not give them to you for this, and I apologize for that. So let's draw out this reaction. We've got 2 H2s, 1 O2. This is going to be a double bond. Again, when we review bonding, you will recall why. And then we've got 2 waters. Now, this is like another question that I think we're going to go over. It gives us the enthalpy of formation of water. We know that it's X, okay? This equation is the formation of water, right? So this enthalpy, X, is the enthalpy of this equation. So this is a situation where you're given the enthalpy of the equation and some of the bond enthalpies, and you're being asked to solve for the HH bond enthalpy. Okay? So what we need to do is set up our equation. So it's the sum of the bonds broken. So we're going to have 2 HH bonds broken. I'm actually going to get rid of that sigma because it makes more sense to just write a bracket there. So 2 HH bonds plus 1 O2 bond, which is Y, minus the sum of the bonds formed, which we have the same bond, but we have 4 of them across our 2 water molecules, so that's going to be 4Z. Okay? That's our equation, and that is equal to X, right? That is, X is the enthalpy of the reaction. Okay? So now all I have to do is solve for the HH bond. So I'm going to take this and bring it over there. And I'm going to end up with 2, I'm rewriting it slightly differently, but I think you'll get the point. Our 2HH is going to be equal to X minus Y plus 4Z. And then we just divide it by 2 and divide this by 2 in order to get the answer. Yes?
So this is like you don't know like what the intermediate step is, so like you have like I'm trying like the energy diagram. It's just like we're going through the product to get to the other step.
All right. This is using bond enthalpy, so it's more like we are breaking all the bonds of our reactants and then forming all the bonds of our products. We know the bond energies for one of our reactants, and we know the bond energies for our products, and we know the total. We know the enthalpy of the reaction. So we're just solving for one of the bond energies. So this is the enthalpy of the reaction. It's given to us as X. Okay? And that's going to be the sum of the bonds broken. We break 2 HH bonds, which we don't know that enthalpy. We break 1 double O bond, which we know is Y. And then we're subtracting out the sum of the bonds formed. All the bonds formed are OH bonds. There are 4 of them in this equation. So it's 4 times Z. So this X equals 2 HH bonds, whatever that is, plus Y minus 4Z. So we're just solving for one of the bond enthalpies. Yeah. Yes, we have to isolate the HH bond. You can assign that another variable like Z or something like that, or I mean, sorry, Q. Yeah. Jacob? Yes, because breaking bonds is always endothermic and forming bonds is always exothermic. So it's going to be reactants positive minus products negative, or reactants same sign and then minus the products. Yeah. That's not to say that the sum of the reactants is always going to be positive, but we are taking that sum as is and we are flipping the sign of the sum of the products. Yes, Braden. Yeah, I moved X over here. I flipped it. Sorry, I set it up so that I would have the thing I'm solving for on the left because that's just how my brain works. But I could have rewritten this as X minus Y plus 4Z equals 2HH, right? And then divide by 2. Yeah. The bracket is just how I separate out the reactants and the products when I'm starting so that I know that it has to be minus this whole thing. It's just, again, it's how my brain works. You don't have to write it like that. And so we just divide both sides by 2 and we end up with 1/2 of X minus Y plus 4Z. Okay? Yep. Nick, you good? Okay. All right, any other questions on this one? Okay. All right, number 11. So this is basically another Hess's law, right? We've got 2 equations, 2 known equations, and 1 target equation. So what we're going to do is we're going to look for the substances of the target equation in our known equations in order to figure out if we need to flip them or multiply them. So I see that I have aluminum, Al by itself, as a reactant, and I see that I have Al up here as a reactant, and that's the only place I have Al by itself. My target has it as 4. The coefficient is 4. In my known, it's only 2. So I know that I'm going to keep this on the reactant side, so I'm not going to flip it, but I am going to multiply this by 2 in order to get to 4 aluminums. Okay? And that means I'm going to multiply this by 2. And then my other reactant is manganese oxide. And I see that that is over here in the products of my second equation. So I know that I'm going to have to flip the second equation. And I'm going to have to change that to a plus. I'm going to have to change the sign because I'm flipping the equation. And I'm going to have to multiply this whole thing by 3. So this is also going to be times 3 because I have 3 MnO2s in my target equation. Okay? So I have to take my known, the whole thing, and multiply it by 3. And once you've figured that out, especially in a multiple choice question, once you've figured out like the locations, what you have to flip and multiply, you don't have to rewrite the whole things out. Like if they're not going to give you something super tricky that isn't going to cancel out. So if you identify, either like 2 reactants or a couple of products, however many things it's going to take you to identify what you need to do with each equation, then you can just take the enthalpies and figure it out. So we're going to have 2 times negative, we're keeping this negative, so 2 times negative 1670, and then 3 times 520, but we're making that positive. So it should be D. Okay. So in the Hess's law practice, I had you write everything out, and cancel everything and make sure that it works out. But when you're given them like this, you can probably just do it on site. You can absolutely write the whole things out and cancel everything, but remember that you only have like a minute and a half per question on paper 1. So, if you can do it faster, do it faster. Braden, you look like you still have a question. Okay. Anybody else questions? Okay. 16. So, here's an excellent chance for us to practice our enthalpy cycle skills. The thermal decomposition of calcium carbonate is this top reaction. That's our target. Calcium carbonate, heat is being added. It's becoming calcium oxide and carbon dioxide. We don't know the delta H for that, but we do know the delta H's for reacting both of our reactants and our products with hydrochloric acid. So, Wiley, since you asked earlier about the cycles, where is my path that I'm taking to go through this cycle? What's the direction that I'm taking? Yeah, the one I'm taking to solve the problem. Yes, well, this is actually not a standard formation or a combustion. This is 2 different separate reactions, but they're both arrows of both are pointing down. But in order to solve it, where does my path have to go? No. So I'm starting here at my calcium carbonate. My path is going to take me down to my pit stop down here, and then back up. So this one is following the direction of the arrow. This one is going against the direction of the arrow. Okay? So we're keeping this and we're flipping this because of the directions of the arrow. Okay? So H1, and we don't have to multiply anything. Even though it says 2HL, that's the thing that we're reacting with our reactants and then reacting with our products to get these. The reactants are not doubled. The products are not doubled. Our original reactant is not doubled, so we don't have to multiply anything by 2. So it should be H1 minus H2 should be A. Right? You don't have to multiply because in neither case are we changing the coefficients of our target reactants or our target products. Yes. You shouldn't in a case like this. I'm trying to think if I've seen an example they've given you that I think if you have to multiply, they're going to put it in that form where they stack the equations for you. They're not going to do that here. I think they just put the two. They needed something. They needed more distractors, so they put the 2's in to see if you would get thrown off by the 2HCl. Don't get thrown off by the acid. It's sneaky that way. All right. Are we good with this? Any other questions? Okay. All right, 17. Why is the value of the enthalpy change of this reaction calculated from bond enthalpy data less accurate than calculated from standard enthalpies of formation? There is an answer here that they are definitely looking for, and I did talk about it in class. What is the correct answer? Yeah, Leon. It is B. Remember that the CH bond is an average of carbon-hydrogen bonds across tons of different compounds. All right? The CO double bond might be different in carbon dioxide versus a compound, so like CO2 is going to be different from a carbon, oxygen, from a ketone, carbon, oxygen double bond, all right, which we'll talk about more in organic, okay? That's going to be a slightly different context than this carbon-oxygen double bond. So that's going to be an average also of all the possible not all possible, but a lot of data that we have about carbon-oxygen double bonds in a bunch of configurations. The H2O bond, we talked about this in class, the enthalpy of this bond is different from the enthalpy of that bond. Because when we break the first bond, we've changed the configuration of things, so the bond enthalpy of the second bond breaking is different. It's lower. Okay, and so we have to average across a bunch of different substances, and that means that we are going to end up with a less accurate value than if we're talking about enthalpies of formation. This comes up again and again in question bank, so I wanted to hammer it home. Yes? It wouldn't. Because it can't be, because it's averages. Because that is the essence of when you get with the bond enthalpies table in your data booklet is average bond enthalpies, because we don't have the enthalpy of that particular bond in that particular molecule. The table would be, like the size of a dictionary, if we were just going to try to do that. So, yeah. Okay, and then 18. So here we are looking for kilojoules per mole. So that means we're going to need to calculate the heat in kilojoules, and we're going to have to calculate the number of moles. All right, so the heat is going to be on top. We're going to use our Q equals MC delta T. Sorry, I just wrote that delta. And then we're going to use our molar mass to find the bottom, right? So we're going to use our Q equals M delta T and then our molar mass. So our M is the 25 grams of the solution, because remember, we're measuring the temperature of the solution, not the temperature of the ammonium chloride. Measuring the temperature of the water in the solution to find a change in heat, okay? We have a decrease in temperature. That means the water is losing heat, which means the reaction system is gaining heat. So again, this is kind of like, gaining, yes, heat. So then the reaction, the enthalpy change is going to be positive, right? Because it's endothermic, gaining heat. Yes? Okay, because we're measuring the decrease in temperature of the water, which is the surroundings. Okay? So the surroundings are losing heat. That is what's sucking the heat out of the water is an increase in energy of the substance going from solid to aqueous. All right, so it's the ammonium chloride that's increasing in energy. And it's taking that energy from the water. So we measure a decrease in temperature of the water, but we're asking for the enthalpy change of the reaction. So if the water is losing heat, the reaction is gaining heat. This, again, it's generally pretty straightforward to think about exothermic reactions losing heat, because we're like, yeah, I can feel it getting hotter. That's release of heat. It's a lot harder to wrap your head around. An endothermic reaction gaining heat means the surroundings get colder, because the surroundings are where the heat is coming from. So when you put an ice pack on your knee after you twist it in a soccer game, hopefully you don't twist your knee in a soccer game, but if you did, and you put an ice pack on it, it feels cold because the heat in your body is moving into the ice pack. Okay? And it's either, if it's regular ice, it's melting the ice, and if it's one of the instant ones, it's fueling the reaction, that it's giving energy to the reaction that's happening inside the bag. Okay? So, this is our delta T. I'm such an idiot, sorry. Today's not, it's been a long week for all of us, I know. This is our C, right? And then this is our delta T. All right, so we've got a number of options here. We've got A is the only one that includes this plus 273. Why would there be a plus 273 there? That's right. They're trying to convert Celsius to Kelvin, but you don't need to, because we have temperature in Kelvin, we have heat capacity in Kelvin, and besides, notice 4.18 joules per gram Kelvin, that's the same as 4.18 joules per gram degrees Celsius. We use the 4.18 all the time. We don't have to convert anything because they're on the same scale, and we are talking about a change in temperature, not an absolute temperature. So we do not need this. And so then we know it's going to be positive, so it can't be B. Okay? So then the question is, we've got 0.1 times 1,000 or just 1,000 on the bottom. Where is the 1,000 coming from? Okay? Yes. So the 1,000 is going to be going from joules to kilojoules, because our reaction is giving us joules, but we're looking for kilojoules in our answer. So it's another little IB units trick. They love to play that. So that's where the 1,000 is coming from. Yeah? Yeah. Because it's kilojoules per mole. Yep. So that means that we need to divide by moles, how many moles we have. So this comes from our 5.35 grams. And we're given the molar mass, 1 mole of ammonium chloride is 53.5 grams, 53.5 grams per 1 mole. And so that's going to be 0.1 moles. So it's going to be our calculated number of kilojoules, our calculated number of joules divided by our number of moles and also divided by 1,000 joules in a kilojoule. Okay. All right. Is good? Any other multiple choice questions that you're like, oh crap, I forgot to ask about that one? Because we're just about out of time, and I think we got through everything that you asked for the multiple choice. So again, I will be here at lunch, and I will make a screencast for those of you who can't come at lunch of all of paper 2. Yes, the answer key is already posted for both of them. All right, guys.